Hey there, curious minds. Welcome to the Deep Dive. We take stacks of information and basically pull out the most fascinating bits just for you. Today, we're heading out into the cosmos. We'll look at how we actually map the night sky, and then dive into some, well, truly mind-bending objects you might not have heard of.
That's right. We've got a great set of sources for this deep dive. Everything from a beginner's guide to star charts to some really detailed observing notes from the Deep Sky Forum. Our mission, really, is to give you a new appreciation for finding your way around up there and, yeah, introduce you to some genuinely strange cosmic sights.
Okay, sounds fantastic. Let's unpack this and get ready to explore the universe, one chart, one weird galaxy at a time. So, all right, before we jump into the really deep stuff, we need to know how to navigate right, and maybe forget your phone app for a minute because our sources actually kick off with the history of star mapping. It goes back, well, over 10,000 years. We're talking cave paintings in France, petroglyphs in America. It's ancient stuff.
It's truly remarkable, isn't it? This very human impulse to look up and map the stars. Our sources mention things like the Zodiac of Dendera from Egypt around 50 BC, a really sophisticated map for its time. It just shows this deep-seated curiosity, this need to understand the heavens.
And what's kind of wild is, even with telescopes and GPS and everything, the basic star chart, still essential for astronomers. No Wi-Fi needed, no battery worries, just a map of the sky lets you find stars, constellations, and those, harder to spot deep sky objects.
Yeah, and what's really clever about them is how they manage to show a 3D sky on a flat piece of paper. Think about it, a brighter star looks like a bigger dot on the chart, even though in reality all stars are just single points of light. Our brains somehow just accept this visual shorthand, this necessary fudge.
Huh. I've never really thought about that specific point. And the way they project the sky onto the flat map, that can be a bit weird too, can it? Like with a planisphere, those star wheels, constellations near the edge get stretched out. They can look totally different from how they appear when they're high up in the sky. That must trip people up.
Precisely. That stretching is, well, it's just an inherent problem with trying to flatten a sphere onto a map. You see it on world maps too. But like you said, it's something you get used to, and a planisphere is still a fantastic tool. And these charts, they show more than just stars. They've got symbols for variable stars, ones that change brightness, and double stars, nebulae, galaxies, a whole language.
Okay, so decoding that language.
Yeah.
How did we end up with the names and labels we use? Our sources point back to Greek times, right? Especially Ptolemy in his huge work, the Almagest, around 150 AD.
Yeah, absolutely. That was foundational. Then, centuries later, it gets translated into Latin in Italy, and boom, we get the Latin constellation names we still use. So when you see something like Ursae Majoris, it literally just means belonging to Ursa Major. It's like a possessive form.
Right, like a celestial address. And then Johann Bayer, early 17th century, he added the Greek letters.
He did, yeah, paying homage to the Greeks. He assigned letters to the brightest stars in each constellation, usually Alpha for the brightest, Beta for the next, and so on down to Omega. Not always strictly by brightness, but that was the general idea. So Alpha Ursae Majoris is Nubhat, the pointer star in the Big Dipper. It's a really neat system.
It is elegant.
And practical, too. For quick notes, astronomers use 3-letter abbreviations. UMA for Ursa Major, ORI for Orion makes things faster. It's a system built up over thousands of years. Quite something.
So if someone listening wants to get started with this, where should they begin? Our sources mention a few good atlases for beginners, Observer's Sky Atlas, star maps for beginners, and maybe something like Starfinder for beginners, to learn star hopping, finding objects by hopping between known stars before getting a full atlas.
Those are great starting points. And for more detail, the Cambridge Star Atlas or the Collins Atlas of the Night Sky are excellent choices too.
Okay, so we've got our maps, we understand the language. Now for the really interesting part. Our deep dive shifts into some seriously wild objects out there. A lot of these come from the Deep Sky Forum's Objects of the Week. It's this amazing online compilation. Really detailed observing notes, sketches, discussions by amateur astronomers.
It really showcases the dedication of the amateur community. It's not just dry data. You get finder charts, images, but also the personal observing notes, the replies, the shared experience. It's like having a whole team of experienced observers guiding you. Invaluable stuff.
Right, let's kick off with a cosmic dance. NGC 2207 and IC 2163 in Canis Major. They call it the Cosmic Ballet.
Yeah.
John Herschel found them way back in 1835. What's the story here?
Well, what's incredible is we're basically watching a slow-motion train wreck. or maybe a merger is a better word. They had their closest pass about 40 million years ago, and they're doomed to merge into one giant galaxy eventually. But right now, the gravity from the bigger one, NGC 2207, is just tearing IC 2163 apart, pulling out these huge, long streamers of stars and gas, stretching 100,000 light years. It's galactic collision in progress.
Wow, so it's a snapshot of galaxy evolution, really. Violent evolution.
Yeah.
Okay, speaking of transformations, let's talk about Keenan's system, Ep.10. This pair, NGC 15216 and 5218 in Ursa Major. William Herschel saw them first, but it took a while to see the connection.
Exactly. It wasn't until 1935 that Philip Keenan noticed something on a photograph. He described this faint but definite band of nebulosity linking the two galaxies, and a little curved arm sticking out. He found the galactic debris left over from their interaction. It shows that even galaxies separated by, 22,000 light years can still be physically connected by these faint bridges. You have to look closely.
Look beyond the obvious.
Okay.
That ties into our next one, NGC 4656. The hockey stick galaxy in Cain's Venatici. It really did look like one. But the story behind its shape got a twist, didn't it? People thought a nearby smaller galaxy, NGC 4657, was pulling it out of shape.
Right, that was the assumption for years. But then newer research, including a paper from '83, pointed the finger elsewhere. Turns out its bigger neighbor, NGC 4651, the Whale Galaxy, is likely the real culprit. And get this, NGC 4657 might not even be a separate galaxy. It could just be a bright knot, a star-forming region within the hockey stick itself, possibly part of the tidal debris. It really shows how our understanding changes as we get better data, better models. We have to reassess.
That's a great example of science correcting itself. Okay, how about collisions that create rings?
Collisional ring galaxies. Yeah, those are spectacular. Ep.219 in Eridanus is one. It's got this huge, incredibly faint outer arc or loop, and you can see the smaller collider galaxy inside it. And then there's VV790b, sometimes called Orion's ring. That one looks like it's maybe happening right now. Observers talk about seeing bright, clumpy sections of the ring in this jet black void in the middle. Really dramatic.
Okay, beyond collision, some galaxies are just weird shapes, like the integral sign galaxy, UGC 3697.
Oh yeah, in Camelopardalis. It's what they call a super thin galaxy, seen edge on, and it's got this amazing S shape. The forum discussions get into how you even classify something like that. Is it impeccable, irregular, Magellanic, peculiar? It challenges the neat boxes.
And speaking of challenges, let's talk about cosmic monsters. M87 in Virgo, home to that supermassive black hole they famously imaged. But it's also a DN. What's a DN?
Right. Dejien double radio source associated with a galactic nucleus. Sounds like something from fantasy, but it's real astronomy. These are only found in elliptical galaxies like M87, always tied to a huge black hole. And they always have two opposing jets blasting out material, creating these massive radio lobes. The jets themselves, like in Quasar 3C405, are thought to be moving at significant fractions of the speed of light.
Wow. And how big do these things get?
They vary hugely. Some are relatively small, maybe 30 light years across, but others, the lobes can stretch for millions of light years, far, far bigger than the host galaxy itself. It shows these black holes aren't just passive objects. They actively shape their surroundings on enormous scales.
That scale is just hard to comprehend. And mostly invisible to our eyes, right? Being radio sources.
Mostly, yes. For visual observers, the key is understanding the physics, seeing those combined radio and optical images. It gives you a sense of the exotic forces at work.
Okay, and sticking with huge radio things, there's UGC 9555 Rose 23 in Boötes, a newly found giant radio galaxy.
Yeah, newly found is the interesting part there. Shows we're still discovering these massive structures. This one comes from a group of 3 galaxies. Material ejected millions of years ago has expanded into these enormous radio lobes. From Earth, they appear about the size of the full moon in the sky, even though they're 750 million light years away. It just keeps pushing the boundary of how big these structures can get.
Incredible. And some galaxies are just hard to see at all, right?
Yeah.
Like Dwingeloo 1.
Ah, yes. In Cassiopeia, a barred spiral about 10 million light years away, discovered relatively recently in 1994. The challenge there is it's hidden behind the dust and gas of our own Milky Way. It's heavily obscured. You really need a good chart just to know where to point your telescope, a real challenge object for observers.
Okay, let's switch focus from whole galaxies to things related to stars, like nebulae. There's H308, the Wolf-Rayet ring nebula in Canis Major.
Right, this is a huge bubble of gas, about 40 arc minutes across, so bigger than the full moon. It was blown off by a massive unstable star called a Wolf-Rayet star, WR6 in this case. Observers using special filters, like an OII filter, can see this ghostly crescent shape, especially the western side, which is brighter. It's a fantastic example of late-stage stellar evolution, how massive stars enrich the space around them.
And another nebula, NGC 6337 in Scorpius, the Cheerio Nebula.
Ah, yes, it gets that nickname because it's a lovely little ring shape. A planetary nebula, much like the famous ring nebula M57. It's fairly faint, magnitude 12.3, and quite small, so it takes magnification well. You can even try to spot the central star.
Okay, but here's one where the story got really interesting. Sharpless 2174 in Cepheus. For a long time, people thought it was a moving planetary nebula. What did that mean?
Yeah, the idea was that the central star, a white dwarf, was moving quite fast across the sky. It had a large proper motion, and astronomers noticed the nebula wasn't perfectly centered around the star, so the theory was maybe the star was moving through space and leaving part of its ejected shell behind it, like a glowing trail. A planetary nebula losing its shape as it moved.
Makes sense.
Yeah.
But that wasn't the final word.
Not at all. This is a great story of scientific reevaluation. Later research, especially by David Frew, looked much closer, and they found a whole bunch of problems with the planetary nebula idea. The white dwarf star. Way too old, like 100 times too old to be the central star of a typical planetary nebula. The gas in the nebula wasn't moving with the star, there was no limb brightening like you'd expect in a shell, and crucially, no sign of a bow shock ahead of the star, which you'd expect if it was plowing through gas.
So if it's not a planetary nebula.
The conclusion was it's actually a Strömgren sphere. Basically, it's just a region of interstellar gas that's being lit up, ionized, by the hot white dwarf passing near it. The gas wasn't ejected by the star is just illuminating existing gas.
Wow. That's a huge shift in understanding, a real aha moment in astrophysics. It wasn't what we thought at all.
Exactly. It shows how science refines itself. We make hypotheses, test them, find inconsistencies, and revise.
Okay, one more stellar site before we move on. NGC 604 in the Triangulum galaxy, M33. An HII region.
Yes, an extragalactic HII region, meaning it's a massive star-forming cloud, but in another galaxy. And NGC 604 is the biggest and brightest one in M33, visually quite impressive. And just to give you that sense of scale again, it's about 1,500 light years across.
1,500 compared to?
Compared to our own Orion Nebula M42, which is maybe 24 light years across.
Whoa, okay. That really brings home the scale difference. Some galaxies have truly enormous star factories.
Indeed. And that leads us nicely into looking at groups and clusters of galaxies.
Right, like the MKW3 compact septet in Virgo, 7 galaxies packed together.
Yes, 7 galaxies all within about 6 arc minutes of sky. It's tiny. And 4 of them form this neat little chain only 3 arc minutes long. It wasn't in the famous Hickson catalog of compact groups, so it kind of flew under the radar for amateurs for a while. Found on photographic plates. It's a good challenge. Some members are pretty faint. And there's a slight puzzle. One galaxy seems to have a much higher redshift, suggesting it might just be in the background, not really part of the group. So maybe it's a sextet +1.
Interesting. And for observers up north, there's Hickson 84 in Ursa Minor.
That's right, a group of 6 galaxies, quite faint, magnitudes 15 to 17. But because it's so far north, near the celestial pole, it moves very slowly across the eyepiece view, which is great if you don't have a tracking mount on your telescope. Gives you more time to study it.
Good practical tip. And there's another chain, the NGC 383 chain, the Pisces group.
Yep, another nice one. About 8 NGC galaxies in a line, ranging from magnitude 12.8 down to 15.5 or so. Definitely doable with something like an 8-inch telescope or larger on a good night.
Okay, zooming out from small groups to something really massive. Globular clusters. But in another galaxy, you mentioned G1 in Andromeda.
Ah, yes, G1, sometimes called Male, too. It's one of the brightest globular clusters belonging to M31, the Andromeda Galaxy. You can see it in amateur telescopes, magnitude 13.2. But here's the amazing part. It's about 3 times larger than Omega Centauri, which is the biggest and brightest globular in our own Milky Way.
3 times larger. That's huge for a globular cluster.
It is, and its metallicity, the amount of heavier elements in its stars, is similar to stars found in the cores of dwarf elliptical galaxies. It makes astronomers wonder, is G1 just a really big globular cluster, or is it something else? Maybe the stripped-down core of a dwarf galaxy that Andromeda swallowed long ago. They sometimes call these objects ultra-compact dwarfs, or UCDs. It blurs the line between cluster and galaxy.
Fascinating. Pushing the definitions again. Okay, one last puzzle to wrap up.
Huh?
The NGC 450 UGC 807 pair in Cetus. a discordant galaxy pair.
Yes, this one's a real head-scratcher. Visually, in a telescope, they look like they're interacting. NGC 450 even has bright star-forming regions, HII regions, on the side facing UGC 807.
Looks like an interaction. Ooh.
But their redshifts, which measure how fast they're moving away from us due to cosmic expansion, are wildly different. The numbers suggest UGC 807 is maybe 8 times farther away than NGC 450, like 484 million light years versus 64 million.
So they can't be interacting.
That's what the redshifts imply. Yet some studies look at the visual evidence, the distorted shapes, and argue they are interacting. Maybe one is a foreground-background object perfectly aligned. Or are the redshift measurements misleading somehow? It's still debated. It's a perfect example of how tricky it can be to interpret what we see, even with modern tools. Sometimes the universe gives us conflicting clues.
Wow, what an incredible trip. From ancient cave painters mapping stars to galaxies doing the cosmic ballet, lawn sprinklers, hockey sticks, giant radio lobes, and even nebulae that weren't quite what we thought they were, and pairs of galaxies that might or might not be interacting. It really shows how much is out there and how much our understanding is still evolving.
It absolutely does. This deep dive really drives home that our picture of the universe is constantly being sketched, erased, redrawn. From basic navigation that started millennia ago to reclassifying objects based on new data. And the thrill of seeing these things, whether it's a faint smudge that's actually a distant galaxy group or figuring out a cosmic puzzle, that's open to everyone.
Absolutely. So whether you're just starting with a star chart or aiming a telescope at one of these faint fuzzies, remember the night sky isn't just static, it's dynamic, full of history, and still holds so many secrets.
And it always invites us to look closer, to ask questions, to compare notes, and to keep refining our understanding.
So what celestial mystery will you try to unpack next? Keep looking up.